Alright, so this video I'm going to go into a little bit more depth on these neural networks, and this is also kind of a test of the new webcam to see if it's actually working in the mic, see if the mic is any good. So I'm going to go into a little bit more detail on these neural networks. I think the last video gave a really good introduction to what the goal is behind machine learning and why we use neural networks and what neural networks are good at doing. Neural networks are essentially an algorithm that allow you to train a model to be able to learn from some input data, in the case of supervised learning. And the way that happens is via some complex mathematics. So I just wanted to dive in a little bit deeper to the mathematics to give you a little bit kind of deeper sense of what's going on and give you a way to appreciate kind of the complexity behind these things. So the last time I presented this picture, which I think is a really good view of a pretty simplistic neural network, actually. It looks pretty complicated from the picture, but this is actually a really simple model. The dimensionality of the input data isn't that large. What do we have? 3, 6, 8 inputs, a few hidden layers, 3 hidden layers, each of size 9, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. And an output layer of 4 values. So, I mean, definitely more complex than the example we were talking about last time, which was the hours of sleep and hours of study, which is 2 input values, and then we had a single hidden layer of 3 neurons, and the output was a single neuron, which was the predicted score. So this one's still a little more complicated than that, but the models that you can, the situations that you can model with neural networks can be much more complicated than this. You wouldn't even be able to create a picture. So again, what I wanted to reiterate here with this slide is that a neural network is actually just a way to represent a series of mathematical operations. So each of these circles is a neuron, which is essentially a computational unit. It stores a value, and all of the values in each layer are connected to the values in the next layer. So if you look at the first neuron here, you see that it's connected to every other neuron in the network. And these things are called weights. In biological terms, it would be called the synapse. But the weight here represents the portion of that particular neuron value that is going into whichever neuron we're looking at. If we're looking at this first connection, we can call this W1 if you want, weight 1. And if it has a value of 0.3, all that means is that 30% of the value from this neuron is going to be transferred to this neuron. And every time there's a connection to a particular neuron, what that indicates is a multiplication of the weight with the neuron value, and then they're all summed up. So again, this is just a big computational graph. That's all a neural network is. It's a bunch of computations happening. So if we go back to the last example, here the y-hat would be the output of the neural network if we were talking about the last example again with studying and sleeping. You see it's just a simple linear combination with a bias added onto the end, and we represented that with a very simple neural network that looks something like this. Each of the connections of the synapses had an associated variable named W1 or W2. These are just the weights. X1 and X2 are the input data, or the input neurons, and y-hat is the output neuron, the predicted test score. However, if we have something more complicated, like this for example, I'm not sure what this could model anything arbitrary. Pick something with 5 inputs and 4 outputs. That's what this neural network is modeling. The equation becomes much longer and much more complicated. So we have to find a way to simplify the representation here. And the way we do that, the way we simplify notation, is we represent the input neurons as a vector, and we usually call that vector x, right? So on the left here, all of these values could be stored in a vector. And the weights in between the layers can be represented as an m by n matrix, where m is the number of input neurons, the number of neurons in the input layer, and n is the number of neurons in the output layer. That's assuming that this is our full network, okay? Let's say that there were multiple layers after this, multiple hidden layers after this with an output layer somewhere down the road. you would still represent these weights as a matrix, but M and N in this case are the number of numbers in the first, quote-unquote, first layer, respectively, and N in the second layer, respectively. So M would be the number of neurons in the layer on the left, N would be the number of neurons in the layer on the right. So we represent the matrix as an M by N matrix. And we usually denote that matrix W. And there's usually a superscript on the W to indicate which two layers you're talking about. For example, W1, 2 would indicate the weights between the first and second layers of a network. And we usually represent the output of a particular neural network as Y hat. Right, so let's continue. Let's take another look at this picture. Again, the output here is Y hat, and we can actually represent Y hat as a matrix multiplication between W and X, where W is the weights matrix and X is the input values, the input neurons. And here I'm assuming this is the full neural network again, and Y hat is the output. I think technically speaking, one of those two vectors, either X or Y hat, should be a column vector. I did not take that into account when I was designing this slide, but it doesn't matter. You get the idea. The idea is that Y hat can be represented, instead of saying W1 plus W1 times X1 plus W2 times X2, like all the way down the list of neurons. It's much easier to write it in a simplified format as a matrix multiplication, W times X. That also makes it very nice when you're coding a neural network, because you can use, for example, most of the machine learning is done in Python, and Python has NumPy, which is an excellent mathematical library, which has matrix multiplication capabilities out the wazoo. So it's really nice that we can express the architecture of this neural network in terms of a matrix multiplication. And the bias, I didn't put the bias in this diagram, I probably should have. But the bias is just a value that is, after this matrix multiplication here, this W times X, the bias is just a value that's tacked on to the final resulting value at each of these neurons in the next layer. So you can think of the bias as just maybe an extra circle, an extra node over here. It's not a neuron, but just an extra value floating out here that's waiting for this matrix multiplication to be done, and then the value of the bias is tacked on to each of the neurons in the output layer. Right. So now we have a very nice simplified way of expressing the interaction between two layers. So I hope that gives you a better idea of what's going on, and maybe a better idea on how to code it if you're not sure how to approach coding neural networks. So again, I like this picture, I like going back to this. And in the first video I had said that there's a lot of complex mathematics that occurs in between the input and the output layers. And what I want to talk about that now. So you understand the concept now that between two layers there's a matrix multiplication that's done, and then a bias is tacked on. Well, that's just a linear combination, right? It's kind of like mx plus b. So in this network, for example, this network with 3 hidden layers, the input layer and the output layer, if we were to propagate some input, these 8 neurons, if we propagated through, there's a wx plus b that's done between the input layer and the hidden layer 1. There's another wx plus b done between hidden layer 1 and hidden layer 2, wx plus b plus for hidden layer 2 and hidden layer 3, and then a final wx plus b between the hidden layer 3 and the output layer. So if that was the only mathematics that we were doing, and that's fine, you could choose to do that. You could make a neural network that just does linear combinations all the way through, but if you're mathematically oriented and you have some experience in math, you would know that all that means is that the input layer, all that means is that the output layer is actually just a big linear combination of whatever the input layer is. You technically wouldn't even need all those 3 hidden layers in the middle. It's just, you could express everything that's happening in the hidden layers as a linear combination between the input layer and the output layer. There would be no need really to have these hidden layers. So the question is, what's happening? Why do we add these hidden layers? The reason that we do that is because we actually, in the hidden layers, introduce some nonlinearities into our model. And that makes the network capable of extracting a more complex mathematical relationship between the input layer and the output layer, which is essentially what we want to do. Real-world data, whether it be, I don't know what you're trying to model, say the stock market, or you're trying to model random motion of things happening in the air, I'm not sure. Whatever you're trying to model using a neural network, chances are there is not simply a linear relationship between the input data and the things that are observed. So we want to introduce some nonlinearity in here. So this picture is very complicated, but what I really want you to focus on in this picture are these symbols right here and here and here. If you can't see the mouse, I'm just going to say it. If we look at layer 2, we've got the neuron value, which I think is denoted B. Oh no, that's the bias. There would be a neuron value in here, but above each of the neurons there is this symbol of kind of like a sigmoidal type picture, this function. Well, what that means is, what the picture is saying is that at each hidden layer, after each linear combination is done, the w.x plus b operation, the linear operation is done, we actually apply what's called an activation function to each of the values in the particular layer that we're talking about. And that happens at every single layer in the stack. So you can imagine we feed some layer and we feed some information, some data into layer 1. And I think in this picture it's denoted as I1, I2, and I3. Those are the 3 inputs into our neural network. We would feed them in to layer 1. And going into layer 2, those values would be, those input values would be stored as a vector, x, and there would be a matrix multiplication done between the weights and that input vector, and then the biases are tacked on. And then there's a value in each of the neurons in layer 2. What we do is we take each of those values and we pass them through an activation function. And this activation function, there are lots of different activation functions you can use. The one similarity between them all is that they are all nonlinear functions. So, for example, and I think you get the point, between every single layer there's an activation function that's applied to the neurons. There are lots of different activation functions. Oops, I changed the style on the slide so it's covering the top, but oh well. There's a unit step, SIG-N, linear. Linear is kind of boring, but piecewise linear, logistic, which is a sigmoid function, hyperbolic tangent. There's a rectified linear unit, which is not on this diagram, but each of these, except for the linear one, I'm not even sure why they put it there, but all the other ones besides the linear are nonlinear activation functions. And the purpose behind it, again, is to introduce some nonlinearity, some complexity into our model. Sigmoid and rectified linear units, which is not on this table, once again, are the most common activation functions used. So a lot of times in a lot of examples that you look up online when you're first designing a neural network, use sigmoidal activation. It's very common in multi-layer neural networks to use a sigmoid function. So that's how we introduce some complexity into the model. And now what I want to talk about is backpropagation. So I forgot to ignore the equations on the bottom for a second. Again, this picture is great. It really generalizes a multi-layered, fully connected neural network. So you've got some input data, you propagate the input data through all the hidden layers, and it eventually gets to the output layer where the neural network spits out some values. In supervised machine learning, that output of the neural network, what you're going to do is compare that output to some labels for your data. For example, in the tests, in the exams example with your hours slept and hours studied, you're going to record that input data for every exam you take, how many hours you slept the night before and how many hours you studied. And you're also going to record the score on the exam that you got. And the scores for each of those associated examples is what's called a label. And you're going to be comparing the labels with the output of the neural network, right? And that comparison is what we call the cost or the error function. How different those two values are is essentially what tells you how accurate your neural network is predicting what you want it to predict. So backpropagation, which I mentioned in the first video, is the method by which we train the neural network. It's one of the methods that we train a neural network with. And the idea is that we can define a cost function or an error function, which is typically the sum of 1/2 times y minus y hat squared. That's one type of error function, where y is the label value and y hat is the output value of the network, right? And the idea, if you're familiar with calculus, is we just want to minimize that cost function with respect to the neural network output, right? It seems easy in principle, but in reality, if you think about it, that output is a function, right, of all of the weight matrices and all of the individual weights in the network. So the y hat is a function of a lot of variables. Okay, this is where even in the example, the small example that we did last time with the input layer of size 2, the hidden layer of size 3, and the output layer of size 1, I'm not even going to count, I think it's 9 different weights, right? Three weights connecting from the hidden layer to the last layer, plus 2 times 3, 6, right? So there would be 9 total weights. So your y hat would be a function of 9 different variables. So it's it's an optimization problem over 9 different variables. If you want to sit down with a piece of paper and a pen and do that calculus, power to you. But the idea is that as these neural networks get more complicated, you've got hundreds, potentially many thousands of variables. It's an optimization problem over thousands of variables, which is why we use machines and GPUs and fast processors to do this work. But essentially, this is what neural networks do. They, in supervised learning at least, they feed some info through a network, some data through a network. You compare the output with what you want the output to be, and then you perform a minimization problem. You perform some calculus, and the weights are all adjusted, and you iteratively repeat this process until you've reached a minimum cost function, so to speak, a minimum cost function with respect to the output. And it's not possible to get perfectly zero, all right, because the real world data that you're trying to model is quite complex. So, but now you have a better idea about what is happening in these neural networks. I hope it was clear. And I'll probably do, the next video I do is probably going to be coding out a neural network in Python. And maybe using TensorFlow, which is Google's machine learning framework. Maybe we'll just make a very simple one by hand. But hopefully this was a little bit more clear and you have a little bit more in-depth knowledge as to what is happening in a neural network.